Greetings. Today I'm going to present you the linear displacement multiplier project. The aim of this project is to design and manufacture a mechanism capable of multiplying a displacement by a factor of 20. We have certain dimensional constraints as well as constraints related to data acquisition from the laboratory setup. Following the step study in the course, we developed the final design, simulated in Simulink, and then proceeded to the PROM facility to manufacture the component using wire electrical discharge manufacturing, or ADM. So to start, we made a functional decomposition of our device. It is consisted of an input mechanism, an output mechanism, the amplification mechanism, and the mounting part. As following, we went to the generation of the QFT, which the requirements describe the goals and the specifications provide the detailed solution. For us, a very important requirement were that it was manufacturable by wire ADM, and specification very important for us was the linearity of device. Here is the complete QFD, and here our system must be able to displace more than the minimum required, using as little material as possible so that the mass of the device is not too high. Other specification we want to give great weight to are the absence of mechanical hysteresis and that it is as thermally independent as possible. Here we have the specification over the specification. This part is important to denote the specification which affect our system the most. From the requirements, very important ones are that are repeatable, small dimensions, readable to the sensor, manufacturable by electrical discharge manufacturing. Then for our customer, the manufacturer, the import my requirements were an easy to manufacture device. The Kelvin clamp we had designed were designed with a 0.5 millimeter distance from the base of support. Then to optimize the use space, we opted for a Y-shaped design. Then the V-grow initially proposed with a trapezoidal shape due to material thickness constraint was then abandoned in favor of a simpler machining process with a generic sizing decided by the manufacturer for all the projects. From the lecture, we have taken inspiration from some concept ideas. Here is the asymmetrical soft spring attenuation, stiff spring attenuation. The concept focus is about having a stable and fixed joint to the support base. Then this was our first design, which consisted of rotating levers. Then our second one is a planar spring fixed to a structure. The sketch focused on the magnifying function. The experiment was experimented to ensure a ratio of 20 to 1. The design could be modified for varying stiffnesses by adding flexure hinges along the dotted lines in the concept sketch in the example. But a big contrary was that a great force was required, however. The third design included flexor hinges to improve the amplification. Then these were some ideas to increase the readability in the input and the output of our demagnifier that sadly then were not able to be implemented. This was also another idea we wanted to implement to increase the range of operation of our device, but was also not implemented at the end. This was our concept 4. This is a system with hinges in which only the use of a leaf spring allowed us to achieve the required stiffness values. Symmetry ensures a linear movement of the output surface, while the lightweight and compact design provides great mobility and effective absorption of the initial displacement. An additional advantage is the alignment of the input and output along the same axial line, which facilitates precise positioning in the laboratory. The proposed system offers several advantages, including ease of manufacture, linear output, and compact yet stiff design. However, there are significant challenges, such as difficult in directly simulating the system and predicting the behavior of the leaf spring due to their non-fixed center of rotation. Additionally, additionally, the weak attachment to the K-clamp support further complicates its stability. To address these issues, we propose replacing the leaf spring with a chain of notches hinges. This was suggested by MATLAB paper, ensuring an equivalent stiffness. However, the solution introduces computational complexity, requiring long processing times and more robust data to validate the approach. In conclusion, while the design is promising in terms of mobility and performance, further refinement and validation are needed to overcome the computational and structural challenges. Then we proceeded to implement a decision matrix. This was used to choose which of the four concepts was the most suitable. In the columns, we have the concept orders from 1 to 4. The first column is the datum, which corresponds to concept 1. Then with the belief map, we could have a resume of an average of our belief maps. So each member draw his own, and then this is the average of all of them. This shows that all our concepts were similar in terms of belief due to them being based upon almost the same principles. So they were all similar and almost equally good. So at the end, the chosen design was a mixture of the third and the fourth. So based on soft spring, stiff spring attenuation principle, the system is symmetrical with the input applied at the center and the output taken from the top left point. So, to control stiffness distribution, the hinges near the output are thicker and stiffer, while the base hinges are thinner and more flexible, allowing for better absorption of the input displacement. Additionally, the design offers modularity in the output, since the top section behaves like a lever. Adjusting its length modifies the output amplitude. Shortening it reduces the output, while lengthening increases it. Given that the lever rotates by only small angle, we can approximate its behavior as linear. The combination of stiffness variation and lever-based modularity ensures a well-balanced and efficient design to our concept. The final design is stiffer compared to the fourth concept, allowing for more precise and repeatable results, even if it was a combination of this design and another. Due to the high number of hinges, the system exhibits some oscillation. However, reducing the number of hinges was not an option, as it would have limited the output displacement, so the output in the input, falling outside the requiring criteria of minimum input of 10 millimeter. That said, when performing tests in a quasi-static manner rather than dynamically, as in the simulation, this oscillation should disappear. This was the simulation of Simulink of our output over the input. And when we calculate the ratio, is consistent with a value of approximately 20. Then the cutting of our system was performed with the electrical discharge machining machine. The main challenges related to this process are primarily associated with its duration, which is influenced by two key factors: excessive ionization of the water in which the machine operates and high number of interruptions caused by short circuits, likely due in part to high conductivity of the water. Then we went to the laboratory to take our test. We randomized measurements between input taken in a continuous manner, steps manner, and the noise in our input conditions. Also, we had issues during the laboratory experience, like the dimension of the V grooves were not fully compatible with the support. Also, due to thickness mismatches affected by the assembly. Mainly was the problem in the V group support. Additionally, we were forced to add a plate under the mechanism, which shifted the center of mass out of our clamp, which was not initially in our design, of course. Then here are the three measurements, three photos that show our mechanisms during the taken of the measurements. We took in total 9 measurements, 3 continuous, 3 step measurement, and then 3 with no input to just measure the noise. Then we went to analyze our data. Here we have some images of our data that was taken in a stepwise manner. Here, the output in red was scaled by a factor of 200 because our design was excessively stiff and it looked like a plain line. Then when we analyzed the continuous taken experiment, we noticed a step during in the output. This can be associated with static friction behavior. So then we measure the noises, mean and variances to determine how much they could go to affect our values at the output. Then we took the mean of the input and the mean of the output and we placed them over a graphic. And the trend shows that to get a significant output, a high enough input is needed. Then from the graph from before, there was the jump that suggested the static friction behavior, which also here can be noticed that if the friction is not overcome, we don't get any output response. So then we tried to do a linear fit regression to test the linear behavior, and from the residual, we see a UV pattern, which suggests an underfit. So we tried to do a higher order polynomial. So with the quadratic regression, we achieved a more accurate representation of the system. And by seeing the residuals, we see no pattern. So our model behaves more quadratic than in a linear way. Then this with the theory of the static friction is also coherent. So by low inputs, we have almost no output response, and the greater the input, the more the output response. Then to exclude that our data is not significantly impacted by the noise, a way to determine it is by checking the variance ratio in percentage between the noise and the mechanic output. When we compute this percentage, we obtain a negligible factor, negligible value. Then here we have the distance radius between the regression and the output value in percentage. This tells us how much in percentage our system is away from the linearity. And here we see great values, which are impacted by the fact that our system is very stiff and the plate under the magnifier is probably causing a friction, which doesn't allow our system to move. Then here we calculated other useful information like the mean of the input over output and the root mean square, which give us also more data of how our data behave. These measurements are in nanometers. Then from the data analysis and the laboratory experience, we can say that our device was affected by a significant component of static friction, which affected the reduction of our system. So to obtain a linearly better result and overcome the issue of the friction, some measures that we've thought about could be add more lubricant so the device can freely slide over the support plate, put a separator between the device and the plate to allow a free movement in the demagnifier, or add more supports to the demagnifier so there is no more need for a support plate which avoids the system to bend over its weight. Here I conclude the presentation. Thank you very much for your time and attention.